Nothing particularly new here. All we're going to see is problem, solution, problem, solution. So I do encourage you to have a look at this problem on the screen, pause the video, give it a crack, and then follow along after that. Okay, so this question here is saying determine the nature of all stationary points. We know that that occurs at f prime of x when the derivative is equal to 0. So when the gradient is flat. And we can see here that this function is a product of two different functions. We've got u being equal to 2x and v is equal to the natural log of x. And so we differentiate the function and that is what we get. We're looking at stationary points, so that's going to occur when the gradient is equal to 0. So I'm going to say let the derivative function equal 0. And so we've got a bit of a simplification going on here, and we get that x is equal to e to the power of -1. That's just by applying our log 2 exponent form there. If we want to have a decimal approximation for this, x would roughly be equal to 0.37. Roughly, if you put it in your calculator and evaluated it, but we are going to keep it as an exact number for the time being. Now, this question is asking us to determine the nature of the stationary point. I'm going to determine the coordinate of the stationary point before I go ahead and examine the nature. And so that's going to require me to substitute this x point into the original function, not the gradient function, the original function, to determine when x is equal to e to the power of -1, what is the corresponding y value. We go ahead and do that. And so I'm just going to write it as log base e, and then instead of putting x there, I've got my e to the -1. This is because when I've got the log base e of -1, I might write it over here, log base e of -1. What I'm going to have is I can bring that -1 down to the front, and so I've got log base e of e, and this thing here itself is equal to 1. So what I've actually got here is I've got this is 2e to the -1 multiplied by -1. And that is going to equal -2e to the -1. And again, if we wanted a decimal approximation for that, that is roughly equal to -0.74. So we've got a coordinate point here, and I might say, therefore I've got the point when x is e to the power of -1, the corresponding y value is -2e to the -1. If I'm keeping them as exact values, or at the point x being equal to roughly around 0.37, the corresponding y value is -0.74. Okay, and I will say that this is a stationary point. I need to determine the nature of this stationary point. So what I'm going to need to do is recognize that the function that I was dealing with is 2x natural log of x, and my derivative function was equal to, let's get it back up here, 2 outside of the log of x plus 1. That was my derivative function. And what I'm going to need to do here is I need to identify, I'm going to use the first derivative test. And what that's going to allow me to do is I'm going to have a look at x points, and I'm going to see what their corresponding slope is. I'm just going to draw up a little table there. And so I've got e to the -1, which I know has a flat gradient. It's got a flat slope by definition of a stationary point. A small value above that, because this is a decimal value there, I'm going to have a 1 there. And now you might be tempted to put a 0 for this x value here, because e to the -1 is stuck between 0 and 1. However, x being equal to 0 is not actually defined in there. The log of 0 is undefined. So what you need to do is you need to pick a number that's smaller. So I might say 0.1. And I'm going to investigate what is the slope doing in order to use the slope, that is the derivative function. So I'm going to substitute these x points into my derivative function. So 0.1 Okay, so I've evaluated that in a calculator and that has told me I've got a negative number, which means that I have got a downward slope at that particular point there. I'm going to do the same thing for the point 1. And that there is going to give me a positive number. And I can do that again by evaluating this in a calculator. Therefore, I've got a upward slope. So I would then conclude and I would say, therefore, the point e to the power of negative 1 and the corresponding y value, which is negative 2e to the negative 1, is a minimum. And we can view this graphically here, where we have got our function, that was our f of x. This is our point that we have evaluated here, right there. And it turns out that that point is a minimum there, where it is roughly, what do we say, 0.3 and negative 0.7. And we can sort of see that there if I erase that. Second question here, again, I do encourage you to read it, pause it, give it a crack, and then follow along and see if you can get the solution out the same as I have. All right, so there is quite a bit going on in this question. I'd probably say it is complex familiar, all right, where we have got a function. And what we're being asked to do here is obtain the nature of all stationary points. And we've got a few unknown coefficients here, unknown parameters, which is k and p, but we've been given a bit of information. We know that we've got a point when x is equal to 2, a corresponding y value is equal to 7, and it actually turns out that that is a stationary point. So that means at the point of the derivative of 2, that's equal to 0, because that's what a stationary point implies. So at x equals 2, we have got a stationary point. That means the gradient is flat. So there's a bit of information to pull out of that guy there. What I'm going to need to do first is I will just differentiate this function I've got here, and I'm going to treat k and p as if they're just numbers. So as if I'm pretending I've got 2x plus 4 over 2x minus 1. I'm going to treat p and k as if they're just numbers. So I take the derivative of kx. What I'm going to be left with is k. Now, because I'm a bit of a goose here, I will elaborate this a little bit more clearly. This function is kx plus p outside of 2x minus 1 to the power of negative 1, just using our index laws there. So if we were to differentiate this guy here, we're going to have that negative 1 comes down, negative 1 comes down, so I'm going to have a minus p there. The inside stays the same, so that's 2x minus 1 to the power of negative 2, multiplied by the derivative of the inside, which is 2. So if I clean up what this derivative should be, what I'm going to get is k minus 2p on top of this business squared. And that's going to be my derivative. Now I've got a little bit of information here. This stuff here is for just the function f of x. That is a point defined on f of x. So I can use this, I can substitute that in. I can say that when y is equal to 7, x is equal to 2. So I've got, instead of kx, I've got 2k plus p over, and when x is 2, so when x is 2, that would be 2 times 2, which is 4 minus 3. So I get that equation there using that bit of information. I can get a second equation here by using my derivative. I know that the corresponding y value of the derivative is 0 when x is equal to 2. So that's, I've got k minus 2p over, and that x value is 2 there. So I've got 2 times 2, which is 4 minus 1 is 3, and 3 squared is 9. So I've got a second equation here by using this bit of information, which is my stationary point bit of information. So I've got 2 equations to solve and 2 unknown values. So I'm going to get to it. So I've just gone ahead and solved my simultaneous equations there. You get p equals 9, k equals 2. There was probably a more efficient way to do it, but it's being done. And so I can then write, therefore, I've got my function is now not kx, but I've got 2x, and plus not p on the top, I've got 9. So that's my function, and I can also actually write out my derivative function, which is f prime of x being equal to 2, not k, I've got 2, and subtract, instead of 2p, I'm going to have 18 on top of 2x minus 1 squared. So I've got a function, I've got a derivative function. Now, let's have a look at what this question is actually asking us to do again. Determine the values of p, k and p, done. Hence, obtain the nature of all stationary points. So this is implying that there's actually more than one stationary point. And we need to then determine the nature of them. So let's have a look at that. We know that a stationary point occurs at f prime of x equals 0. So that means we've got 0 equals 2, subtract 18 over this stuff. And let's just go ahead and solve that. So we go ahead and solve for our x there, and we see that we've got x equals 2 and x equals negative 1. We already knew that this was a stationary point. We've actually got the other y value. We knew that that was a stationary point, gave us in the question. So now what I'm going to do is I'm going to determine the coordinates of this guy right here. Now I'm going to go ahead and do that. So I'm going to sub x equals negative 1 into f of x So just with a bit of substitution there, I can see that I've got the stationary point at negative 1, negative 5. Now this question, all it's asking me to do is, or even is the question, there it is, determine the nature of all stationary points. So I'm going to again use the first derivative test. And we know we've got the function fx is equal to 2x plus 9 on 2x minus 1. And we've got our derivative function. It's always nice to just write them down again and remind yourself. You've got 2. And I'm just going to write up a slope table again. Except this one's going to be a little bit extended because I need to determine the nature of all my stationary points. Now I knew I had stationary points at, let's draw another one on here. I knew I had stationary points at negative 1 and 2, and they were both flat by the definition of a stationary point as flat. So now we're going to put in some nice numbers here. We're going to put in negative 2, we're going to put in 0, and we're going to put in 3, and we're going to observe what is the slope at each of these points to see if we've got maximums or minimums or points of inflections. We need to substitute these into the derivative. So I've got f prime of negative 2 first is equal to 2 minus 18 over, and I've got 2 times negative 2 will be negative 4 minus 1 will be negative 5 squared. That's 25. That is a positive number. Therefore, I am increasing. Now I'm going to find out what's going on at the point 0. What's the slope doing? So I've got 2 subtract 18 over, that's going to be negative 1 squared, which is 1. That is equal to a negative number. 2 subtract 18, that's negative. So slope is now going down. And then we've got a conclusion here. We can say, therefore, the coordinate negative 1, negative 5 is a max because our slope was going up, then it was flat, then it's going back down. That's what our derivative table has told us there. And get rid of that, what I've just written there. We've got the last one to evaluate here. F prime of 3 is equal to 2 minus 18 over 2 times 3 is 6. Minus 1 is 5. It's 5 squared on 25. Positive number. It is. It's a positive number. And so this slope will then start increasing at this point, and we can determine that that is a minimum. So we'd say, and the point 27, that was the stationary point given as the question, is a minimum. And we are done.